Starting in autumn of 1609, Galileo conducted observations of the moon, of which he made some drawings of striking impact. In open contrast to the Aristotelian tradition, which held that the celestial bodies are perfectly smooth and spherical, the surface of the moon, observed through the telescope, showed cavities and prominences. Galileo had also noted the presence of small luminous zones in the dark part of the lunar disk in proximity to the terminator, the line of separation between the lighted part and the one in shadow. As dawn broke over the lunar surface, the luminous spots melded with the illuminated zone. Galileo correctly attributed this phenomenon to the presence of mountains, whose high peaks are touched by the sun's rays before the terrain below them, exactly as happens on the earth, when at dawn the mountain tops are already lit by the rays of the sun, while the valleys are still shrouded in darkness. With a simple but ingenious method, Galileo was able to calculate the height of the mountains on the moon. He estimated the distance of a mountain from the terminator as about 1/20th of the apparent diameter of the moon. Then, dividing by 20 the length of the true lunar diameter, known since antiquity, he obtained the length of the segment FA. By applying Pythagoras' theory to the right triangle GAF, he found the hypotenuse FG. It represented the distance of the top of the mountain from the centre of the moon. By subtracting from this the radius of the moon, he obtained the height of the mountain.
After discovering Jupiter's moons, Galileo tracked their movements for several days. To measure with precision the distance of each satellite from the planet, Galileo designed a device known as a micrometer. Giovanni Afonso Borelli described the micrometer as a rule with 20 equal divisions. The device was fitted on the telescope and could slide along the body tube. Galileo observed Jupiter's system through the telescope with one eye, while his other eye watched the micrometer lit by a lantern. He then set the micrometer distance so as to make the interval between two divisions of the graduated scale coincide with the planet's apparent diameter. This procedure enabled Galileo to superpose the telescope's field of view on the micrometer. He could thus determine the distance of each satellite from the planet, with the radius of Jupiter as the unit of measurement. In January 1610, while exploring the heavens with his telescope, Galileo discovered 4 small star-like objects around Jupiter. Having soon concluded that these were the planet's satellites or moons, he sought to establish their orbits and periods. The velocities of orbital motion decrease from the innermost to the outermost moon. All 4 display almost the same brightness. It was difficult, therefore, to work out which was which and calculate how long they took to complete their orbits around the planet. To determine the positions of the moons without having to perform complex calculations each time, Galileo developed a diagram, a sort of analog calculator, called the Giovelabe. The design shows Jupiter and the orbits of the 4 moons to scale. The orbits are placed in a grid of parallel vertical lines spaced at intervals equal to the radius of Jupiter. While making his telescopic observations, Galileo would estimate the apparent distance of a moon from a planet in units equal to Jupiter's radius. The intersection between the vertical line corresponding to this distance and the circle representing the moon's orbit gave its position instantly. By means of a thread, one could read the value on the marked scale drawn in the margin. However, the moon's observed positions vary with the relative positions of Jupiter and the Earth in the course of their revolutions around the Sun. For example, the timing of a moon's passage in front of Jupiter, as seen from the Earth, differs from the timing of the same phenomenon if it were observed from the Sun. The time difference depends on the Earth-Jupiter-Sun angle, known as the annual parallax. To cancel this continuously variable effect, Galileo recorded the motion of the moons relative not to the Earth, but to the Sun. To avoid complicated calculations, he developed a second diagram consisting of a representation, to scale, of the orbits of Jupiter and the Earth around the Sun. Jupiter is assumed to be immobile at the moment of the observation. The diagram features a graduated scale giving the Earth's position relative to Jupiter. The parallax value could be read instantly on another graduated scale. The two diagrams were combined into a single instrument, known as the Jovilabe. Jupiter's position at the moment of observation was computed by means of a rotating disk. A moving pointer, fixed with an arm to the instrument's plate, served to determine the Earth's position at that same moment. The arm thus represents the Earth-Jupiter link, that is, the observer's continually changing line of sight. The parallax value for any position of the Earth relative to Jupiter could be read directly on a scale on the upper rim of the instrument.